Thank you very much. I'm actually very grateful also to Professor Alok Mishra for organizing this meeting and for asking me to participate in it. I'm also very thankful to Professor Nimai Singh for taking the pains to spell out my full name. And that itself shows why it is not desirable to use it often. It is used in my passport, yes, but I almost never use it anywhere else. Thank you very much. Can we go to the next slide, please? Can we go to the next slide, please? Yes, thank you. You see, for people of my generation, for physicists of my generation, Professor Mitra was an inspirational figure. And his personal example as a physicist and his values in physics and his ideals were something which motivated many of us. I realize that I'm somewhat of an odd man out in this gathering because I'm not his direct student. I'm not a particle physicist. I work in another subfield of physics. I would like to talk a little bit about some recent work which I have done with two colleagues in this field. Before that, I would like to share two reminiscences of Professor Mitra. One is the following. I think sometime in the mid-1990s, I became aware that Professor Mitra, after retirement, was actually staying for a short while in the Institute of Advanced Studies, which at that time was directed by Dr. Raja Ramanna. I very quickly contacted him and requested that his unique knowledge be shared with students. And I arranged for a course on nuclear physics to be given by him in the Indian Institute of Science, which happened. And that was the formal connection. But then since actually our contact goes back to that with his father and my father-in-law and so on, there was a lot of personal interaction. Secondly, I came into close contact with him when he was editing a book which was mentioned by Professor Panchapakeshan, which is on India's contribution to physics, which is a part of a huge multi-volume enterprise by Professor Chattopadhyay on the contribution of India to history, philosophy, civilization, science, etc., etc. In this context, Professor Mitra suggested that I should write an account of the Indian contribution to condensed matter physics, which I was happy to do. And this went on for actually several years. And finally, it was published. And as Professor Panchapakeshan said, it is well buried. I mean, it's hardly anyone knows about it and knows about the book because it's an extremely expensive book, which is in many volumes and not very easy to access. But that association was very important to me because it came at a very important stage in my life. Now, what I would like to do in the next several minutes is to talk about some preliminary work on a possibly paradigmatic limit of the behavior of electrons in metals. In this limit, electrons are actually mobile, they move around, but so they are globally free, but locally they are very unfree in the sense that if two electrons happen to be nearby, then the repulsion between them is extremely strong. Now, in order to sort of motivate this limit, I would like to start with the opposite limit, which is the free electron limit, which almost all of us are familiar with. Could we go to the next slide, please, Professor Mishra? Yeah, thank you. Well, this is a limit which was proposed in 1900 by Drude. It's a very extremely unreasonable proposal. He proposed 3 years after electrons were established to be a common constituent of matter, that metals consist of a free classical gas of electrons. Now, this is extremely I think it's hard to believe because, it was clear to everybody, including him very strongly, that electrons are very strongly tied to the parent ions from which they originate. They also interact with each other. The Coulomb repulsion is not switched off. And therefore, to regard them as free is somewhat unrealistic. Not only that, it was not clear which electrons were to be considered free, which were to be considered unfree. But he argued that maybe the valence electrons should be considered as free because they enter into chemical bonding. Now, with this extremely simple hypothesis of assuming that all the valence electrons in a metal are to be considered as constituting a completely ideal classical electron gas, he was able to successfully explain many electrical and optical properties of metals, including using the kinetic theory of gases idea, except that in this case, the elementary constituents, the particles are charged. He could explain Ohm's law, he could explain skin effect, and what at that time was considered a very great success. As a matter of fact, Albert Einstein thought that this was the greatest success of this Drude picture. He was able to show that a particular ratio of thermal conductivity to the electrical conductivity divided by temperature is a universal constant. This is called the Wiedemann-Franz law. This universal constant for an ideal quantum gas is known to be pi square by 3 kb square by e square. But he was, of course, a generation before the quantum revolution, and he got 3 by 2 kb square by e square in classical, using using the ideas of a classical gas. Now, this ratio is almost right, partly because two factors of the order of 100 cancel each other. And also, I think because at that time, the electron charge was not particularly reliably known. Electron charge was known to an uncertainty of about 20–30%. So that gave an error of about factor of 2. And with all that, he was able to compare his this number with the experimental value, and it turned out to be in fairly good agreement with what is known, and it was considered a great success of the theory. So let me go to the next slide, please. Yeah. Yeah. Now, this kind of approach has several problems, some of which I mentioned. One of them is that we don't know which electrons are considered to be free. He assumed that these are valence electrons. Now, of course, we know that, yes, these are electrons in the unfilled shells, and these are indeed valence electrons or holes. He also assumed that these electrons form a classical gas. We know that, they form a degenerate quantum gas of fermions. If you assume a classical picture, which he did, which he had to, then you find that the specific heat from the Dulong-Petit law is proportional to the Boltzmann constant. Whereas in reality, if you assume it to be a quantum gas, it is proportional to the Boltzmann constant times T by Tf, and this is indeed what is observed. The most worrisome problem was the pretense that electrons don't interact and form an ideal gas. They actually interact with the lattice ions and with each other. And there are many very sophisticated, adiabatically connected, successful theories of interacting electrons with interaction effects, which are described by a few parameters like the effective mass and so on. So this is the Fermi liquid theory of metals, which is the canonical theory, which we use all the time. Can we please go to the next slide? Yes. So it is now believed that electrons in a metal form an interacting Fermi liquid. This is not a Fermi gas. This interacting Fermi liquid is a coherent Fermi liquid for temperatures much lower than the Fermi temperature. It has well-defined quasi-particles. It has well-recognized collective excitations. It has a superconductive instability for effective electrons between these effective attraction between these quasi-particles. Now, that is where matters stand as far as this limiting paradigmatic behavior picture of electrons in metals is concerned. However, it turns out that there is a large class of systems and phenomena in metals where the interaction between the electrons is the dominant thing. That is, the repulsive potential energy of interaction between the electrons is much larger than the kinetic energy of electrons. But in spite of the fact that this is so, the thing is a metal with mobile and kinetic electrons. So there are many ways of putting it. You can say that electrons move while strongly avoiding each other. You can say somewhat more formally that these are strongly correlated electron systems and so on. So the obvious question is there an opposite paradigmatic limit which is natural for such a system in which electrons are locally unfree but globally free? So that is, see, if the interaction between the electrons is very strong, then you cannot treat it as a perturbation on the motion or the kinetic energy of the electrons. So is there a non-perturbative limit which we can use, which is also metallic? Well, I will describe a tentative attempt to understand and describe this limit in a lattice model for electrons. This is work which I have been doing with Professor Hassan of the Institute of Mathematical Sciences in Chennai and Professor Vidyadhiraja of JNC in Bangalore. This was published last year, the first paper. Can I please go to the next slide? Yeah. Now, to start with, of course, we start with the Hamiltonian. Well, the Hamiltonian is written there. It is the energy of an electron, which is sitting at a lattice site I, when it has spin sigma, it has energy epsilon I. For a homogeneous system, epsilon I does not depend on I. It is the same at every site. If two electrons happen to be on the same site, and from the Pauli exclusion principle, they have to have opposite spin, then they repel each other with a strength U, which is positive. U can be small or it can be large. The kinetic element, the motion of electrons, is provided by the fact that an electron from a site I can hop to a site J and vice versa. So this is known as the tight binding model of an electron system. That is, you have the electron tightly bound to the lattice site, but hopping quantum mechanically from one site to another. The U is an oversimplification. The fact is that the effective interaction between the effective Coulomb interaction between two electrons in a metal is short-ranged, because though the bare interaction is long-ranged, the effect of other electrons is to screen this bare interaction and make it short-range. So we go to the opposite limit. We assume that this interaction is zero range. That is, unless the two electrons happen to be on the same site, there is no interaction. And this is somewhat of a an oversimplification, but it turns out that we can't solve this model either, because even though it looks very simple. Can we go to the next slide, please? Yeah. So this model is extremely well known. It is known as the Hubbard model. It is actually exactly soluble in one dimension, and it's also exactly soluble in all dimensions if the interaction is zero, interaction vanishes. When the interaction vanishes, you have a collection of independent electrons, and this is just what I said. It's a tight binding version of the free electron gas. Now, if the interaction is non-zero, and if you treat the effect of this interaction as a kind of a perturbation on the kinetic motion caused by non-zero Tij, then the substance is a metal at all filling. But this cannot be always right. For example, suppose the filling were half. That is, suppose there were exactly 1 electron per site. Suppose the electron density is such that there is 1 electron per site. Now, if the repulsion between the electrons is very large, then it is energetically favorable for electrons to stay at their sites and not move. And such a thing is an insulator. So the ground state is an insulator. Such an insulator is known as the Mott insulator. This has a qualitatively different many-body wave function. But then you can ask the following question. This is actually a very different but a somewhat simple limit. But suppose the filling is not half. That is, suppose you don't have exactly 1 electron per site, which means that there are some sites which have electrons and some sites which do not have electrons. Then it has to be a metal, because an electron can always find a neighboring site which has none, and so can hop to it and so on. So then the question is, what kind of a metal do we have in that case? And all experimental facts point to its being a somewhat strange metal. It has a characteristic coherent Fermi liquid behavior at extremely low temperatures. On the other hand, it is an incoherent Fermi liquid over a very wide range of temperatures. And how does this incoherence manifest itself? It manifests itself in the fact that there are no quasi-particles. That is, if you have a particle of a given momentum, momentum is a good quantum number within the Brillouin zone vector, modulo the Brillouin zone vector. If you have an electron with a well-defined momentum, it should have a well-defined energy. It turns out that this is not true, but if it were true, then the spectral density would be a delta function. In reality, the single particle spectral density is very broad, so there is no quasi-particle. Another experimental feature which is very odd is that a clean metal in this family has a resistivity which is linear in temperature. Now, it turns out that clean metals which are Drude-like, they also have non-zero resistivity. Like, copper has non-zero resistivity, platinum has non-zero resistivity at non-zero temperatures, and so on, even when it is very clean. And that is due to the interaction between the electrons and the lattice vibrations. Here, that resistivity is most likely very small, but in spite of that being so, there is a very large linear in temperature resistivity for clean systems. This particular feature has been very extensively studied in cuprates, and recent experiments are unearthing more and more strange aspects of this linear resistivity. So what have we done? We have tried to see whether this incoherent Fermi liquid regime can be explored in an opposite limit. That is, whereas in the Drude free electron limit, you are essentially assuming that the electron repulsion U is 0. let us see whether we can do something about describing in a generic way what the behavior of the system is when the interaction between the local repulsion between the electrons is infinitely strong, that this is the opposite limit. So it's not clear at the moment whether we can do it and whether we can say that this is a paradigmatic limit, which is an unfree electron limit relevant to the large family of strange metals, and so on. Well, that's our aim. I will describe a tentative approach to the infinitely strongly correlated electron limit. Please go ahead. Yeah. To describe this limit, we use a very simple representation, which was again due to Hubbard, which is called the Hubbard X operator representation in this subfield. Basically, you have at a particular site I, these Hubbard operators XIAB, where basically the this operator is this ket times this bra. The complete set of states at each site is given by what A can be. A can be 0, 0 meaning no electron at that site. Up meaning one upspin electron at that site. Down meaning one downspin electron at that site. Now, you cannot have at this particular site a state in which both up electron and down electron live together. If U is equal to infinity, then that is infinitely high in energy, and therefore it is removed. So there are only 3 states possible per site. And so you have a lattice, you have a space of states in which at each site there are 3 states, and you have a product of all this. So the Hamiltonian is an operator which lives in that space of states. What is the Hamiltonian now? That also we simplify. We assume that it costs 0 energy to occupy an electron state. So epsilon is 0. Mu is the chemical potential. This is the only variable in the system, actually. Depending on the value of the chemical potential, you have the occupation number varying from 0 to 1. Occupation number meaning the average fractional electron number per site, average. It is not that electrons are fractionated, but this can be any fraction. This average can be any fraction. Then you have a hopping. So this describes the hopping. Describes the hopping from a state sigma at site I to another empty site state at site J, again with the same spin. So this is an extremely simple Hamiltonian, and it would have been exactly soluble if this were a canonical fermion creation operator. Unfortunately, it is not. And so this cannot be solved. This has not been solved exactly, and we are still struggling with how to solve it. We simplify this even further. We say that the hopping is non-zero, an electron hopping is non-zero between one site and another only if these are nearest neighbor sites. This is simply because hopping is via the overlap of quantum mechanical wave functions, and the wave function overlap is becomes rapidly very small as distance increases, and therefore the only sensibly non-zero, essentially non-zero, unavoidably a non-zero overlap which has to be included is between nearest neighbors. So it's actually, so this model is characterized by 1 energy parameter and actually 2 energy parameters, but this energy parameter is basically related to the occupation number. Now, there is, as I said, there is no small parameter in this theory. There is no perturbative expansion. Now, this model has been studied actually in great detail by Shriram Shastri starting 2010. Using the Schwinger source method. That is, he adds to this Hamiltonian a source term and then takes various derivatives with respect to the strength of the source, and then finds different kinds of coupled equations for Green's functions, and then reduces the source strength to zero. Okay, so there is a whole set of papers. I mean, there are, I think, at least 700 pages of papers, starting with this, and then also one more recent version is in 2022. What we have done is to study the same Hamiltonian in a slightly different method. We use what is called an equation of motion method. That is, we find the equation of motion for different correlation functions like XX correlation functions, which could be fermion correlation functions or boson correlation functions and so on. And we use the infinite dimensional approximation. This is a very successful and defensible approximation for real systems, which are of dimension more than one. We use this approximation to decouple the equations of motion for Green's functions, and then we solve these equations self-consistently. Can I have the next slide? Yeah. So the crude physical idea is the following. If an electron moves, then it necessarily gives rise to local bosonic fluctuations. This is what I have tried to show here on the right-hand side, where I have showed that suppose an electron hops from one side to the next side. Then at this side, the electron number changes or the spin changes, and therefore there is a bosonic fluctuation produced here. And then at the next side, the next nearest side, the electron is there, and therefore there is an electron, the electron propagates there. So basically, we say that the electron motion gives rise to local bosonic fluctuations, and the propagation of bosonic fluctuations depends on electrons. And for this purpose, for this reason, self-consistently finding the correlation function is very crucial. And which is what took us a long time. It took us almost 2 years. So I will just present some results. One of the results is the following. We have calculated, for example, the single particle Green's function of Green's function. Its self-energy, the imaginary part of its self-energy for small energies or frequencies should go as frequency squared. That is a signature of a coherent Fermi liquid. We do find that that's what happens. For example, this inset shows the plot of the imaginary part of the self-energy as a function of frequency for different dopings. You can see that at extremely low frequencies, it is parabolic, that is proportional to omega square, but then very quickly it becomes linear. Here we have shown also the real part of self-energy, which ought to be linear, which it is if it's a quasi-particle. So the behavior of imp sigma as omega square, behavior of real sigma as omega for small omega is a signature that you have quasi-particles. And you actually do have quasi-particles at extremely low temperatures and extremely low frequencies. So let me go ahead, please. If I have the next slide, I can show more. So, you know, while obtaining this result, we found that there are sort of inevitable local bosonic fluctuations of local charge or local spin with which the electrons are coupled. I have shown here the spectrum of local bosonic charge fluctuation at a doping, I think, of 2 or so for different frequencies and temperatures. You see, at the lowest temperature, it's extremely sharp. As the temperature increases, this bosonic fluctuation becomes somewhat broader. It is highly asymmetric. It has a sharp rise followed by a rather broad, gentle decay. Now, this is an intrinsic bosonic fluctuation spectrum, which can be identified as a kind of an intrinsic quantum noise in the system. So let me go further. Please go ahead. Next slide, please. If I can have the next slide. Yeah. So this fluctuation, well, it doesn't look like anything which we know in the sense that it is not it doesn't have a simple form. We have tried to fit it to a kind of a Lorentzian form, but it has a much longer tail than a Lorentzian. So we have tried to wrestle with this local bosonic fluctuation spectrum in many ways. One of them is to calculate the mean energy. So you calculate the mean energy of this fluctuation, which is omega, and we show it as a function of temperature here. Omega is on this side and temperature is on this side. By the way, all energies like omega, T, and so on, they are shown in dimensionless numbers. The dimensionless number means this energy is divided by another energy, which is the hopping energy. Now, what we see is that at low temperatures, the mean energy of bosonic fluctuations is higher than the temperature. So we, using a naive identification, which is very common, we say that this is the quantum regime where the mean energy of these fluctuations is much larger than or larger than the temperature. We find that, yes, there is a regime where the mean energy of fluctuations is larger. Then at a higher temperature, it becomes smaller than the temperature. So we show that result in the next slide. Can we have the next? Yeah. So here you see that the three regimes, one which is confined to extremely low temperatures, where the imaginary part of self-energy and the real part of self-energy are those which correspond to a canonical Fermi liquid. That is shown here, the Fermi liquid regime as a function of doping and temperature. You see that it is there at all dopings, but at extremely low temperatures. Below this temperature, it is a Fermi liquid, and above this temperature, it's an incoherent quantum liquid. We call it incoherent quantum regime. As you increase the doping, this temperature increases. And above this temperature, you have what is called the classical regime. In this classical regime, it is easy to describe qualitatively the goings on. You can say that, well, in this classical regime, each electron is basically not hopping. It is sitting at a particular site. And if there are, let us say, 0.6 electrons per site, then 0.4 sites have no electrons, and 0.6 sites have electrons, either of upspin or downspin. If the system is paramagnetic, the number is equal. And obviously, if you have a lattice, there are a large number of arrangements of this kind, and that gives you the entropy of the system. So this entropy is also very well known, and if you can calculate this entropy. So this is an entropy of charged systems, and therefore it should be relevant in thermopower. And indeed, it turns out that in strongly correlated systems, the thermopower reaches this classical limit at surprisingly, astonishingly low temperatures, and the value which it has is roughly the same as what you would have if you assume the electrons to be classical non-hopping, strongly correlated objects, 1 electron per site. Yeah, can I have the next slide, please?
Sir, please wind up. So 10
Wind
minutes
up.
more.
Okay, oh, I'm running. Okay, then I'll wind up. So let me just wind up by saying that we have also calculated the resistivity. We show that the resistivity is T square at low temperatures. It is linear at most other temperatures. There are two regimes. This is one linear regime. There is another linear regime. There is a crossover. Let us go ahead. And we don't understand this either. Let us go ahead. Yeah. Next slide, please. Yeah, so we believe that we have unearthed two crucial features of extremely correlated Fermi liquids. One is strong local diffusive self-generated bosonic fluctuations coupled to electrons, and another is a large incoherent quantum regime. We do not know what the origin of this extremely low temperature is. The theory is extremely opaque. It is very complicated. We need a simpler, clearer theory. We do not have it yet. This is for a u equal to infinity. Unfortunately, all systems have finite u. And even the strongly correlated systems in which u is very large, by which I mean u by t is larger than 10, u is finite. So we have not yet developed, and we are at the moment we are in the process of developing a theory which is of first order in 1 upon u, that is first order in t upon u, which is a small parameter. Please go ahead. Next slide, please, and I think I'm done. Yeah. So we are generating this, trying to develop this 1 upon u perturbation theory. We know that there is a 1 upon u expansion which eliminates the high energy excited states, and so there is an effective low energy theory which is correct to order 1 upon u. Not an easy theory, and we don't know what to do with it. At the moment, at least we don't have any concrete results. However, many years ago, we had developed a phenological theory with that is we meaning here Sumilan Banerjee and Chandan Das Gupta and myself, which seems tantalizingly close to what one expects of this 1 upon u theory. Thank you very much.
Okay. We can have 1 or 2 questions or feedback. So please, from the audience.
Is it okay, Professor Nima, if I could ask one question?
Please.
So, Professor Ramakrishnan, this may be a not very well formulated question. I apologize in advance. But what I was wondering was that are there, I mean, it may not be even directly related, but it basically hinges on this idea of dealing with the non-perturbative systems or working in the non-perturbative regime. So I was wondering, are there any kinematophysics systems which have, dare I say, a u going to 1 over u symmetry or a modular symmetry involving u? Is it a strong weak coupling duality? Any system in kinematophysics which has strong weak coupling duality as a symmetry?
I think the Kondo effect, for instance, is a kind of a model in which, as you change the energy scale, there is a logarithmic increase in the effective coupling constant, and it becomes an extremely strong coupling system at very low temperatures, which is somewhat like gauge theory of strong interactions.
I see. Thank you.
Okay. Any more question? Otherwise, we can thank the speaker. Or any question? Other?
Professor Panchpageshan has a question.
Please.
Yeah, I have a question which is not closely related. What happens to things like Anderson localization when you consider these kind of theories?
Yeah, this is a theory for all right. Anderson localization is something to do with a strong disorder effect, effects of disorder. This is for a very clean lattice system, in which a homogeneous clean lattice system. So that's the lawyer's answer. The real answer is I don't know. Also, that generally people believe that if there are strong correlations, localization effects will be enhanced.
Thank you.
So now we have, let us thank the speaker, Professor T.V. Ramakrishnan.